Well, welcome. This lecture is going to be on specific energy, and it's not going to be my usual polished lecture where I'll be filling in notes and you can fill them in as I go. I'm just showing you notes that I've given in past years, and you're going to have to pause the video from time to time and write the notes in that are there, or just kind of write as I go. So last time we talked about some of the basics of open channel flow and about some of the characteristics in general, like depth, top width, hydraulic radius, etc. And today we're going to be talking about specific energy. And the definition of specific energy is the total head with respect to the channel bottom. We remember the EGL is a plot of the total head with respect to some horizontal datum. Here we're going to be talking about something like the EGL. It's a plot of the total head, or it is the total head, but the datum is the channel bottom, which is going to be in open channel flow almost always sloping downward. So it's the sum of the pressure and the elevation head and the dynamic head in an open channel. It's the distance between the channel bottom and the EGL. And the equation for it is specific energy is equal to y, the depth, plus v squared over 2g. Now, remember, that the EGL is going to be z plus y plus v squared over 2g, but in this case, if you're along the channel bottom and you're saying how much head do I have relative to that, the z is just always the channel bottom. If you go above that, then you've got some depth and you've got some velocity head, and those are the two terms. We can also replace v with q over a, and so sometimes we use this form, y plus q squared over 2g a squared as well. This version down here, you can see, looks a lot like this one up here, but here we've replaced big Q with little q, and on the bottom, big A with y. So in a rectangular channel, in other words, a channel that has a rectangular cross-section, there's this term little q, which is the flow per unit width. So per width of the channel, there's a flow rate per that width, and we call that little q. And so if we replace, if we say, well, then big Q is equal to little q times W, and we replace big Q in here with little q times W, we can do some math and geometry and come up with this equation here. Okay, so this one is only valid for a rectangular channel. This is sort of the general form. Both these two are the general forms that we're going to be using. For uniform flow, for a given flow rate, the total head can decrease, right? The total head, if you're flowing downhill, the total head is decreasing. We're losing energy, but we're not losing specific energy. In uniform flow, the depth is constant and the velocity is constant all on the channel. And if depth and velocity are both constant, then the specific energy is not changing, okay? So that's a characteristic of uniform flow, that we're not changing our specific energy. In other kinds of flow, in varied flow, we are changing our specific energy. And so we'll be using that later in this lecture to kind of look at varied flow situations and use specific energy to predict what's going to happen. Here the notes quality is pretty low, so I'm going to switch over to this version real fast. We plot these specific energy curves, and this diagram is showing you the cross-section of an irregular channel with three different possible depths, right? These three aren't all happening simultaneously. There are three different options for the depth. The same flow rate is going through all of these. Remember that in an open channel, we're not constrained like we are in pipe flow. So we could have, for the same flow rate, different depths. And if for the same flow rate the depth is higher, then we're going to have a lower velocity than if for that flow rate the depth is low and we have a higher velocity. And this is actually what comes out of plotting these specific energy curves. This is a plot. Y, or depth, is along the y-axis, and along the x-axis is the specific energy, E. And so we're not used to, we're not used to plotting things like this where, you know, E is the x over here, and then y is going to be on the y-axis. So we kind of have to flip this, isolate y, plot it as a function of E, but you can see y is kind of showing up sort of in both places, right? So it turns out that when you plot this thing, it actually kind of looks like this. And you can do it for basically plugging in different values of E and then solving for y to plot this. You can also do it the other way. You can plug in different values of y and then find values of E and plot them. And this is what it looks like. It's this kind of horizontal-ish hyperbola, parabola-looking thing. And what comes out of doing this is you can see that for a given specific energy, we have two possible depths in general that we can be at. We have this one down here and this one up here at the same specific energy. This one up here is high depth, which would give me low velocity, and this one is low depth, which would give me high velocity. You can see also on this graph is plotted this diagonal line. This is a one-to-one line where basically y equals E. Okay, so we go up here. Sorry, keep going doing that. E equals y, this term, plus this term, or E equals y plus this term. So if I plotted the diagonal, which is E equals y, that's one of the two terms. And then we have the v squared over 2g. So you can see on this plot, y equals E. Then if I add, again, the v squared over 2g, I get to my actual specific energy line. So y plus v squared over 2g. So you can see here, this is a lower velocity, right? This v squared over 2g is the distance between that line, the horizontal distance between the line and the specific energy curve. That's lower up here than it is down here. It's making up a bigger portion of the specific energy down here than it is up here. And indeed, that's that's what's happening is as you make the depth higher, if specific energy is conserved, that is going into depth, whereas if you make the depth lower, that energy is going into velocity. So there's an exception to the two possible depths rule, which is right here at the apex. This is the minimum specific energy possible for this flow rate, and it happens at something called critical flow or critical depth. So if you look over here, there's an equivalent depth in this channel for all of these, and at the critical flow here, there's y sub c, which is what we call critical depth. It's the depth that occurs at the minimum possible free energy, and there's only one possible depth there. So this is in general what we're going to be working with. You'll want to continually refer back to this graph to understand what's happening, and we will as we go. This one is just to show you that, hey, those specific energy curves are specific to a certain flow rate. If I change the flow rate, I will get a different specific energy. So for a given flow rate in a given channel, I have one specific energy curve. For that channel, if I increase the flow rate, I'm increasing the energy that's available, and so this specific energy curve shifts to the right. And we'll talk about these here in a second. So these two alternate depths, the high depth low velocity, the low depth high velocity, they have the same specific energy, and we call them supercritical and subcritical flow. Supercritical flow is going to occur in this bottom section of the specific energy curve. The low critical depth, so just focusing here on the Q1 curve, if we are anywhere below this critical depth, we're in the supercritical flow range where depth is low and velocity is high. If we're anywhere above this critical depth, Then we're in the subcritical flow range where depth is high and velocity is low. All right. And we will be talking over the next couple of class periods about when we'll expect supercritical flow versus subcritical flow. We'll be talking about it actually in this lecture a little bit, how to change between them, how to predict what's going to happen when you do, etc. We can force from one flow character or one flow type into another, though it might not stay that way. So here's an example of a sluice gate that's put in the flow. So the flow is going from left to right, hits the sluice gate, and we might transition from subcritical flow upstream of the gate to supercritical flow downstream of the gate. When we do that, it could be the case that we stay in supercritical flow. It could also be the case that the supercritical flow will return to subcritical flow via hydraulic jump, which we'll also talk about in a few lectures. And because we haven't covered uniform flow yet, we don't quite have all of the tools yet to be able to predict under what circumstances it will stay and under what circumstances it will not stay. But we will soon. When we cover uniform flow, we'll come back to this and we'll talk about how does that uniform flow concept come into play with this concept. How do we merge the two in order to make predictions? Also, when we're in the lab playing with the lab flume, we'll also mess with things like the slope and the flow rate to also try to experiment and see under what conditions we see different of these happening. Then there's critical flow. So we've got subcritical, supercritical, or critical. Those are our three possible options. And critical flow occurs, again, when the specific energy is at a minimum for a given discharge. So here we're going to consider, this is our general equation for any channel. And if it's a rectangular channel, then we can replace A, the cross-sectional area, with BY, okay? So A squared becomes B squared Y squared in the denominator. And then I'm going to take the derivative of the specific energy, DES, with respect to Y, because that's how we find mins and maxes, right? We take the derivatives, we set them equal to 0, and then we solve. So we're going to take this equation, the derivative with respect to Y, here's Y, and here's Y, and set it equal to 0, and then solve for Y. So here, this equation, derivative of Y with respect to Y is 1, and then here we're going to have a negative Q squared, and then because we've got the 2 in there, it's going to multiply by this 2 and cancel it out, and then GB squared YC cubed. So I've added a C subscript to the Y because we're saying this is, now we're solving for critical depth. We're in this situation where specific energy is at its minimum, so the specific Y we're solving for is the critical depth. So given this, then I can isolate Y sub C, and it's the 1/3 root, the cube root of Q squared over GB squared. Now this is only valid for a rectangular channel because of this substitution I made in here. But this is the equation we'll use for finding the critical depth of a rectangular channel. You can see if the flow rate goes up, the critical depth goes up. If the flow rate remains constant and B, the width, gets bigger, then the critical depth goes down. That is, again, for rectangular channel only. We'll talk in a minute about the general case of solving for critical depth. We definitely do not want to use this equation if we have a trapezoidal channel, for example. Also, sometimes, again, because big Q is flow per unit width, we can replace a Q squared over B squared. Again, B and W are used interchangeably as the channel width. Then we get Y sub C equals little q squared over G to the 1/3. So then, recognizing that Q equals A V sub C, where V sub c is the critical velocity. So since there's a critical depth, there's also a critical velocity. And again, in a rectangular channel, we replace A with By, then Q equals By V sub c. If I plug into this equation for Q, By V sub c, and simplify and isolate V, I get that V sub c equals the square root of Gy sub c, or V equals the square root of Gy. So the critical velocity can be just solved for as G times the critical depth. And this is really useful, and it's interesting that the only thing that the critical velocity depends on is what the critical depth is. So for whatever the critical depth is, we can automatically know what the critical velocity is in a rectangular channel. And in fact, this can be shown to be generally true, actually, for any channel. And it's really interesting because I'm not sure if you covered this in fluid mechanics or not, but that this is also the velocity of a low amplitude surface wave. And so what this means is, if let's say I was standing in a shallow pond or a deep pond, and I dropped a pebble in the pond, and I make ripples. Ripples are low amplitude surface waves, right? They're not large ocean waves that are going to like break and crash, but they're low amplitude surface waves, and they're going to move out at some velocity. What is that velocity? It's the square root of Gy, where y is the depth of the water I'm standing in. So as the water gets deeper, the velocity of those ripples are going to go faster, and that's all that that velocity depends on. It doesn't depend on how hard the pebble hits the water or anything else. It just depends on the depth, which is very interesting. And so looking then at this, what this means is, let's say I was standing in a channel, and I was standing now not in a pond, but I'm standing in a creek, and it's flowing, let's say, from this way to this way. And it's flowing at the critical velocity. All right. So when I drop a pebble in that creek, ripples, if it was going really slow or stagnant, ripples would go both ways. When the velocity is going this way, it's going to tend to, at first, at low velocities, just compress the ripples that want to go upstream and elongate the ones that are going downstream. If I'm at the critical velocity, if this is moving at the critical velocity, and so the depth is the critical depth, the velocity of the low amplitude surface wave is this, which, again, if I was standing in still water, would go both ways at that velocity. But if I'm standing in water that's moving at the critical velocity this way, the waves that want to go upstream are wanting to move upstream, but they basically can't. So at this velocity, the V sub c this way cancels with the V wanting to go this way. And so the waves will just stand still, and none of those ripples can propagate upstream. Okay? They'll all go downstream, basically. So that's the transition point where if it's moving slow and I drop it, again, some ripples can go up and some can go down, even though the ones going up are going to go slower. As the velocity gets higher and higher, at some point, all the ripples go downstream. And that's at that critical depth, critical velocity. This is important in open channel flow because if I put in any kind of obstruction in the flow, if I do something to the flow, when I do that, the information that thing is there, the effect that has on the flow and on the water can propagate in both directions when I'm in subcritical flow. When the velocity is low, I do something to the flow, and the effect of that is going to be transmitted both downstream and upstream. Right? The ripples can move upstream. If I'm in supercritical flow and I put in some control on the flow, I do something to the flow, the information about that cannot propagate upstream. It can only propagate downstream. Now, so think about that. We've got supercritical flow upstream. I do something to the flow. It's going to communicate what I did, the ripples, the waves, everything that effect has is going to be downstream but not upstream, unless I can somehow transition to subcritical flow upstream. Then possibly that information can propagate. And we'll talk about this more in a lecture or two when we get to flow profiles. We'll show that this is the case. But for now, just kind of keep that in your mind. Controls on supercritical flow are upstream of the supercritical flow section. You can't control supercritical flow from the downstream side. In other words, you can't force supercritical flow upstream of an obstacle. You can force supercritical downstream of an obstacle, and in fact we showed that here, right? We forced the supercritical flow downstream of the sluice gate, but we can't force supercritical flow upstream of a control. We can force subcritical flow upstream of a control, and that's what this means. Controls on subcritical flow can be, and typically are, downstream of the subcritical flow section. Okay, so we'll talk about flow controls later more, but one thing I didn't mention earlier, the critical depth, Y sub C, can be shown to be 2/3 times E sub C, or 2/3 times E min. So going back up to like this graph, or this horrible graph, this location right here, E min, is going to be that the critical depth is 2/3 E min. So go here, this critical depth is, this distance right here is 2/3 times the distance from here to here. All right. So no matter where this specific energy curve lies, there's always this 2/3 relationship between critical depth and E min. And we'll use that in an example problem at some point in the future. Okay, so finding critical depth for the general case. We talked about how do you find critical depth for a rectangular channel. There's a general equation that applies for all cases, including rectangular as well as trapezoidal or any channel section, which says that at critical depth, this is true. Q squared over G equals A cubed over T. Okay, so this is not generally true all the time, but when we're at critical flow and depth, this is true. All right, so T is that top width. And so how do we actually solve using this? Where does the critical depth actually show up? Well, the critical depth shows up usually in the equation for the cross-sectional area. If this was a rectangular channel, A could be written as BY, and then you could solve for Y. In that case, T in a rectangular channel is also equal to B, so that's helpful. But in a trapezoidal channel, T is not equal to B, and so, but there is a relationship between T and, say, the depth, given the characteristics of the trapezoidal channel. And I'm going to give a handout that shows some of those helpful relationships soon. And then A, the cross-sectional area of the trapezoidal channel, obviously is going to be dependent also on the depth, Y. And so if you replaced A with an equation for A as a function of Y, you could then solve for Y. Now, usually this is like implicit in Y sometimes, but you can at least try values for critical depth and calculate these and verify that this is true. In the rectangular channel case, I don't think you have to iterate, but in the trapezoidal channel case, I believe you do. Once you replace A and T with formula for the area and the top width of the trapezoid as a function of Y. Okay. Yeah, we already talked about finding critical depth for rectangular channels. All right, so let's look at an example problem. On the left-hand side, this is just finding critical depth for a rectangular channel. We've got an 8-foot wide rectangular channel. The flow rate is 100 CFS, and the bottom slope S sub 0 is 0.0004. Calculate the critical depth. Well, this is a rectangular channel, so all we do is plug and chug. Y sub c equals cubed root of q squared, 100 CFS squared, over g, 32.2, times the bottom width squared, 8 feet squared, and we get 1.69 feet. We'll talk about this later. That when I used to teach uniform flow earlier, this is the same characteristics for one of our uniform flow problems. And so you see y sub n, which is a normal depth, has already been calculated here, and we compared it to y sub c. We'll talk about that later. Over here, we're saying this is a trapezoidal channel. Now we want to solve for the critical depth. It's 20 feet bottom width. The side slopes is 2 horizontal to 1 vertical, and the flow rate is 500 CFS. Calculate the critical depth. Okay, so again, since this is true at critical depth, we can also say that q squared t over ga cubed equals 1. Right? I've just multiplied, basically cross-multiplied q squared t, and then divided by a cubed over ga cubed equals 1. And then I'm plugging in the flow rate 500 here. T, this is an equation for the top width of a trapezoidal channel as a function of y, the depth. So it's the bottom width plus 2 times the side slope number here times the depth. And again, I'm going to give you these relationships in a handout. The old book had them in it. The new book, I don't think, has a super convenient way of getting them. Divided by g, 32.2 times a cubed, and again, this right here is an expression for the area of a trapezoidal channel as a function of y. So it's the bottom width plus 2y times y, and then cubed for the a cubed equals 1. And so I can plug in different values of y here and iterate and solve for it as 2.46 feet. Okay, now we're going to talk about the Froude number. So Froude number is dimensionless number like the Reynolds number, and it's defined as the velocity divided by the square root of gy. So Reynolds number is the ratio of the inertial forces relative to the viscous forces, and the Froude number also is sort of relating to kinds of forces, but has more to do with gravity. So v over square root of gy, but another way of expressing it is the square root of q squared t over ga cubed, which you might recognize all of this, right? So here, this part looks a lot like this, right? So all I'm doing here is dividing both sides by the square root of gy. So I get v over square root of gy. That's the Froude number. Okay? And then the other one looks a lot like this, right? And you'll see why in a second, because the Froude number is helpful in predicting what flow range we're going to be in. Are we in subcritical flow, critical flow, or supercritical flow? You can see here on the diagram, if our Froude number is less than 1, if this thing is less than 1, we're going to be in subcritical flow up here, right? Our velocity is low at subcritical flow. Our depth is high, so this thing gets low. Froude number is less than 1. If our Froude number is greater than 1, i.e. velocity is high, depth is low, then we're going to be down in this range, in supercritical flow range. And if Froude number is equal to 1, we're at critical flow. So that's what we were talking about, right? V sub c equals square root of gy sub c at critical flow. At critical flow, this is equal to this. In other words, the Froude number is 1. This whole thing is 1 at critical flow. Not always, but at critical flow. And that is equal to this thing, which again we said this thing is equal to 1 at critical flow. That's what we said right here, at critical depth, critical flow. So again, the Froude number is equal to 1 at critical flow. This diagram too, I just wanted to highlight one other thing. So we've got the Froude number ranges shown on here. And you see this thing down here too, right? This is plotted at a negative depth. And this is going to be important to recognize that this thing exists, because it turns out, going all the way back to the beginning, this thing, while it looks like it would just plot like this, it's actually kind of like a cubic relationship, because y is showing up here and in here. And so it turns out that for a given specific energy, there aren't just 2 solutions to this equation, there are 3. And you can see down here that that's the case. For a given specific energy, you've got the subcritical flow solution, the supercritical flow solution, and the negative depth solution. I don't know what a negative depth is. Nobody knows what a negative depth is. So we just ignore that this thing is even there. It doesn't make any sense. And so when we are solving specific energy problems, sometimes we have to solve for the depth given a specific energy. And when we do that, we have to recognize that there are 3 possible solutions, and the negative one we will ignore. Okay. Now, talking about moving on this curve, I mentioned that in uniform flow, the specific energy is constant. Okay. So whether I'm in supercritical flow or subcritical flow, if I'm in uniform flow, I'm not moving from that value of specific energy. However, if I'm at varied flow and I'm kind of moving along, like say we look at these cases, so here I'm not in uniform flow because my depth is not constant. Here I'm definitely not in uniform flow. I have a depth here, I have a depth here, I have a depth here, it's changing. So as my depth changes, we'll talk later about hydraulic jumps and kind of show that they actually do lose energy, but maybe this one's more helpful. My depth is going from high to low. I might not be actually like losing any energy overall, but I'd be going from depth high to depth low, and I have to stay on this curve. So if I'm going from here to here, and I have to stay on the curve, that means I have to go around. So I have to pass through critical depth in order to get to this lower flow. The lower depth. Likewise, if I wanted to go from supercritical here up to subcritical here, I would have to pass through critical depth on my way there. All right? And this term accessibility says that the upper limb, the subcritical flow limb and the supercritical flow limb, they're not accessible to each other unless there's a local restriction in the flow. I have to move along the specific energy curve to get from one limb to the other. And if I change the specific energy, I could have a situation where something in the channel changes, and I might say I go from here to, maybe I don't go to this depth. Maybe I actually lower the specific energy. And I am starting here, and I lower the specific energy to a lower value. There's 2 possible depths at that lower specific energy, but if I want to get to either of them, I have to go this way. I have to go left along the curve. And as soon as I get to one that is at that specific energy, I stop. In other words, if I'm lowering the specific energy from here, the bottom part of this is not accessible to me, because as I start going towards that new point, I'm going to pass through a point that satisfies the specific energy equation. I'm going to stop. All right, so I would go from this depth to this depth, stay in subcritical flow, not go all the way around supercritical. If my depth goes if my specific energy goes up, it could be the case that, again, if I don't put a control on the flow, and we'll talk a little bit more about this later, I would just go from here up to a new situation that satisfies that equation. I would have to do something to force myself through critical depth, and if I did, then I could get to supercritical flow and get to that range down there. So part of why we're talking about this is because engineers, civil engineers, we occasionally want to get to change the flow from one regime to another for one reason or another. One example of this is spillways in dams, or even really steep stormwater outfalls, where we want the water to be moving quickly. All right, and if we want the water to be moving quickly from a high elevation to a low elevation, we want things to be really steep. But if we make things really steep, the flow is going to go supercritical, which is fine. But if we make our infrastructure really steep and then we reach like a river or a creek down here that the flow is still at supercritical when we hit there, there's going to be a lot of erosive force, a lot of velocity, a lot of chance of scouring that channel. We might not want that. So we might have cases where we want to force the flow from our supercritical flow that we wanted it in to get moving to a subcritical flow, where we'll get the velocity to drop and lower that erosive force, lower the stress on the channel sides, and get it in a subcritical flow range. So we're putting, again, things in place. We're putting controls to force flow from one regime to the other. Likewise, in these cases up here, why would you want to do this? This kind of thing, a sluice gate, sort of the same idea as like a dam, where this happens a lot when you have irrigators, farms that have like an intake for their pump in, say, an agricultural canal. And you want to back up the water to make sure their intake is always submerged. You could put like a little check dam in there, a little dam that has a weir, flow over the top or something. That's one option, but then you're going to get silt accumulating behind the dam, and maybe that's okay, maybe it's not. A sluice gate has the advantage of backing up the water for that intake to go in, but keeping silt able to be moved down the channel. So you see sluice gates a lot in agricultural situations. Backs up the water like we want it, but then it creates this supercritical flow section, or could. And if this is a natural channel, again, we might not want to erode away the natural channel. So we might want to create this, but then get it back to subcritical flow while we're still on concrete, for example, while we're in an area that's protecting the channel bottom. Force it back to subcritical flow, then let it go back to the natural channel where it's a little bit slower. So that would require, we've got the sluice gate, but then it might require something else to trigger this back up into subcritical flow. Energy dissipation blocks, for example, are a common one that can be put on the channel bottom. Okay, so that's accessibility. So let's talk about channel transitions. This will be probably the last part of this lecture. When we talk about channel transitions in this class, we're going to be talking about two specific kinds of things. One is a change in the bottom elevation of the channel, so we call it a step. It can be a step up or a step down. And the other is a change in the channel width. It can be a narrowing or it can be a widening. And we can use specific energy concepts in order to predict what's going to happen when we go through a widening or a narrowing or a step up or a step down. Okay? So, a couple rules. In a channel width constriction or widening, the specific energy is not going to change, but the critical depth is going to change. Okay? So again, let's look back up here. Let's assume we're in a rectangular channel because it's easier to see this. Let's see. in a rectangular channel, if I change B, if I change the width of the channel, my critical depth will change. But given my original definition of specific energy, nothing in here is necessarily specific to the channel width, even here. Doesn't have anything to do with that. So I change the width, and the specific energy doesn't change, but the critical depth does. Versus the other option, which is in a sudden vertical step, the critical depth is not going to change, but the specific energy is going to change. So the rule is whatever the specific energy is before the step plus Z1, where Z1 is the elevation of the channel bottom, that's going to equal the specific energy after the transition plus Z2, where Z2 is the elevation of the channel bottom after the step. So in other words, like if I say Z1 is equal to 0 in this case, and Z2 is equal to 1, then E2 has to drop, because then it's going to be E1 equals E2 plus 1. So E2 is smaller than E1. All right. So let's look at that in this example problem. We've got a rectangular channel, 7 feet wide, flowing along. It's 6 feet deep here, and then it encounters a 1-foot step. The flow is moving along at 4 feet per second, and we want to know what is the depth of flow over the step. What does this depth turn out to be? And you can see the answer already written here, but let's try to solve that. And it turns out, as you'll see, the depth actually drops. Okay, if the depth didn't change, if this kept going kind of straight, and it's 6 feet here, and we go up a foot here, then it would be 5 feet here. But it does change, and it actually lowers to 4.9 feet. Why? Well, you'll see, but the velocity is going to go up, and so some of that energy goes into velocity and drops the depth. So we're saying through a step, the specific energy changes, and we've got this. So let's look at what is the specific energy before the step. E1 is equal to Y1 plus V1 squared over 2G. I can calculate that out, and I get 6.25 feet. I now use this equation and say, hey, E2 is equal to E1 plus Z1 minus Z2, and we're going to call Z1 0 and Z2 1. So 6.25 minus 1, and E2 is 5.25 feet. I lost a foot of specific energy because of that step. Okay, so if E2 is 5.25 feet, we want to know what's the depth in that second section. So here's our general equation for specific energy. I want to solve for Y2. I also don't know velocity here because I don't know the depth. So if I use this one, again, since it's a rectangular channel, I can use this form, replace V with Q over A, and replace A with B times Y. I have this, so then I replace this with, I know this is the flow rate because Q equals AV, and we said it was 6 feet deep before the step, 7 feet wide, and 4 feet per second. So 168 CFS goes up here. B is 7, and then we've got Y sub 2, and then plus Y sub 2 here. So 5.25 equals this. And again, you can't solve for Y2 directly here. So you either need to plot this. So if I plotted this as like Y equals, and then in my calculator I could put all of this with like this as x squared plus x, and then subtract off the 5.25. I could plot it and then find the intercepts. And again, I'm going to have 3 intercepts for that. One of them is going to be negative, and then I'll have 2 others. And if I'm starting, the 2 others I'm going to have are likely, because I'm dropping in specific energy. I'm going from 6.25 to 5.25. I'm going to the left. So this is a situation where, in all likelihood, I'm going from here down a little bit, and I'm going to get 3 possible solutions, and this first one I reach is going to be the one that I end up at. So my solutions are, there's a negative, there's a 1.6 feet, and a 4.9 feet. Again, I get directly over this step. I'm at 5 feet because I was at 6 minus 1. I'm at 5. I start dropping, and I hit 4.9, and I'm done. I never get to 1.6 because only 4.9 is accessible to me. And that is my noon depth, and I'm done. So that's channel transitions. On Friday, I might do some more example problems that are some more channel transition stuff. I might also just move into uniform flow, or I might try to do some of both. So that's all for this lecture, and I will see you soon.